I'm walking around in the circle of life, doing the things I know, walking the same ways 100 times.
You feel me? Yeah. You feel me? Nah, that's real. Keep it on West Coast, because I feel like cats don't show us the love out here. Dago, putting on for the town. Tell me about it.
Buenas, buenas. Bueno, voy a estar viendo los últimos dos videitos de árbol binario y después voy a tratar de comenzar los proyectos. Así que bueno, vamos a parar la música un toque. Vamos a subir esto para que se escuche bien el video. Vamos a poner esto por acá y vamos a ver esto.
In this lesson, we are going to write code for level order traversal of a binary tree.
Okay.
As we had discussed in our previous lesson, in this lesson, we are going to write code.
Okay, ahí.
In this lesson, we are going to write code for level order traversal of a binary tree. As we had discussed in our previous lesson, in level order traversal, we visit all nodes at a particular depth or level in the tree before visiting the nodes at next deeper level. For this binary tree that I'm showing here, if I have to traverse the tree and print the data in nodes in level order, then this is how we will go. We will start at level 0 and print F, and now we are done with level 0, so we can go to level 1 and we can visit the nodes at level 1 from left to right. From F we will go to D, and from D we will go to J. Now level 1 is done, so we can go to level 2. So we will go like B, E, G and then K, and now we can go to next level A, C, I, and finally we will be done at H. This is the order in which we should visit the nodes, but the question is, how can we visit the nodes in this order in a program? Like linked list, we can't just have one pointer and keep moving it. If I'll start with a pointer at root, let's say I have a pointer named current to point to the current node that I'm visiting, then it's possible for me to go from F to D using this pointer because there is a link. So I can go left to D, but from D I cannot go to J because there is no link from D to J. The only way we can go to J is from F, and once we have moved the pointer to D, we can't even go back to F because there is no backward link from D to F. So what can we do to traverse the nodes in level order? Clearly we can't go with just one pointer. What we can do is, as we visit a node, we can keep reference or address of all its children in a queue, so we can visit them later. A node in the queue can be called discovered node, whose address is known to us but we have not visited it yet. Initially, we can start with the address of root node in the queue to mean that initially this is the only discovered node. Let's say for this example tree, address of the root node is 400. And I'll assume some random addresses for other nodes as well. I will mark a discovered node in yellow. Okay, now initially I'm enqueuing the root node, and by storing a node in the queue, I'll mean storing the address of the node in the queue. So initially we are starting with one discovered node. Now as long as the queue has some discovered node, at least one discovered node, that is as long as the queue is not empty, we can take out a node from the front, visit it, and then enqueue its children. Visiting a node for us is printing the value in that node, so I'll write F here. And now I'll enqueue the children of this root node. First I'll enqueue the left child and then the right child. I'll mark visited node in another color. Okay, now we have one visited node and two discovered node. And now once again we can take out the node at front of the queue, visit it, and enqueue its children. By using a queue, we are doing two things here. First of all, as we are moving from a node, we are not losing reference to its children because we are storing the references. And then, because queue is a first in first out structure, so a node that is discovered first, that is inserted first, will be visited first. So we will get this ordered that we are desiring. Give this some thought and it's not very difficult to see. Okay, so now we can dequeue and visit this node at address 200. And once again, before I move on from this node, I need to enqueue its children. So now at this stage we have 2 visited nodes, 3 discovered nodes, and 6 undiscovered nodes. And now we can take out the next node from front of queue. We'll visit it and enqueue its children. If we will go on like this, all the nodes will be visited in the order that we are desiring. At this stage we can dequeue node at 120, visit it, and enqueue its children. So we will go on like this until all the nodes are visited and the queue is empty. After B we will have E here. Nothing will go into the queue this time. Next we will have G here, and the address of I will go into the queue. Now K will be visited. Now at this stage we have reference to 3 nodes in the queue. Now we will visit this node at 320 with value A. And then we have C, and now we will print I, and the node with value H, the node with data H will go into the queue. Finally we will visit this node, and now we are done with all the nodes. The queue is empty. Once the queue is empty, we are done with our traversal. So this is the algorithm for level order traversal of a binary tree. As you saw in this approach, at any time we are keeping a bunch of addresses in the memory, in the queue, instead of using just one pointer to move around. So of course we are using a lot of extra memory, and I'll talk about the space complexity of this algorithm in some time. I hope you got the core logic right. Let's now write code for this algorithm. I'm going to write C++ here. This is how I'm defining node for my binary tree. I have a structure here with 3 fields, one to store data, and the data type is character this time, because in the example tree that we were showing earlier, data type was character. And we have 2 more fields that are pointers to node, one to store the address of left child and another to store the address of right child. Now what I want to do here is I want to write a function named level order that should take address of the root node as argument and print the data in the nodes in level order. Now to test this function, I'll have to write a lot of code. To create and insert nodes in a binary tree, I'll have to write some more functions. I'll skip writing all that code. You can pick the code for creation and insertion from previous lessons. All I'll write is this function, level order. Now in this function here, I'll first take care of one corner case. If the tree is empty, that is, if root is null, we can simply return. Else, if the tree is not empty, we need to create a queue. I'm not going to write my own implementation of queue here. In C++, we can use the queue in standard template library. And to use it, first we'll have to write a statement like hash include queue here. And now I can create a queue of any type. In this function, I'll create a queue of pointer to node with a statement like this. Now, as we had discussed earlier, initially we start with one discovered node in the queue. The only node known to us initially is the root node. With this statement queue.push root, I have inserted the address of root node in the queue. And now I'll run this while loop, for which the condition is that the queue should not be empty. And what I really mean here is that while there is at least one discovered node, we should go inside the loop, and inside the loop we should take out a node from the front. This function front returns the element at front of the queue, and because the data type is pointer to node, I am collecting the return of this function in this pointer to node named current. Now I can visit this node being pointed by current, and by visiting, if we mean reading the data in that node, I'll simply print the data. And now we want to push the addresses of children of this node into the queue. So I'll say that if the left child is not null, insert it into the queue, and similarly if right child is not null, push it into the queue, or rather push its address into the queue. And I'll write one more statement to remove the element from front of the queue. With call to front, the element is not removed from the queue. With this call pop, we are removing the element. Okay, so this is implementation of level order traversal in C++. You can check the description of this video for a link to source code, and there you can also find all the extra code to test this function. Let's now talk about time and space complexity of level order traversal. If there are n nodes in the tree, and in this algorithm visit to a node is reading the data in that node and inserting its children in the queue, then a visit to a node will take constant time, and each node will be visited exactly once. So time taken will be proportional to the number of nodes. Or in other words, we can say that the time complexity is big O of n. For all cases, irrespective of the shape of the tree, time complexity of level order traversal will be big O of n. Now let's talk about space complexity. Space complexity, as we know, is the measure of rate of growth of extra memory used with input size. We are not using constant amount of extra memory in this algorithm. We have this queue that will grow and shrink while executing this algorithm. Assuming that the queue is dynamic, maximum amount of extra memory used will depend upon maximum number of elements in the queue at any time. We can have a couple of cases. In some cases, extra memory used will be lesser, and in some cases extra memory used will be greater. For a tree like this, where each node has only one child, we will have maximum one element in the queue at any time. During each visit, one node will be taken out from the queue and one node will be inserted. So the amount of extra memory taken will not depend upon the number of nodes. Space complexity will be big O of 1. But for a tree like this, the amount of extra memory used will depend upon the number of nodes in the tree. This is a perfect binary tree. All the levels are full. If you can see, as the algorithm will execute at some point, for each level, all the nodes in that level will be in the queue. In a perfect binary tree, we will have n by 2 nodes at the deepest level. So maximum number of nodes in the queue is going to be at least n by 2. So basically extra memory used is proportional to n, the number of nodes. So space complexity will be big O of n for this case. I'm not going to prove it, but for average case, space complexity will be big O of n. So for both worst and average cases, we will be big O of n in terms of space complexity. And when we are saying best, average and worst cases here, it's only going by space complexity. Time complexity will be big O of n for all cases. So this is time and space complexity analysis of level order traversal. I'll stop here now. In next lesson, we will discuss depth first traversal algorithms, pre-order, in-order and post-order. This is it for this lesson. Thanks for watching. In our previous lesson, we talked about level order traversal of binary tree, which is basically breadth first traversal. Now in this lesson, we are going to discuss these three depth first algorithms: pre-order, in-order and post-order. I have drawn a binary tree here. Data type filled in the nodes is character. Now as we had discussed in earlier lessons, in depth first traversal of binary tree, if we go in one direction, then we visit all the nodes in that direction. Or in other words, we visit the complete subtree in that direction, and then only we go in other direction. In this example tree that I have drawn here, if I'm at root and I'm going left, then I'll visit all the nodes in this left subtree, and then only I can go right. And once again, when I'll go right, I'll visit all the nodes in this right subtree. If you can see, in this approach, we are reducing the problem in a self-similar or recursive manner. We can say that in total, visiting all the nodes in the tree is visiting the root node, visiting the left subtree, and visiting the right subtree. Remember, by visiting a node, we mean reading or processing the data in that node, and by visiting a subtree, we mean visiting all the nodes in the subtree. In depth first strategy, relative order of visiting the left subtree, right subtree, and the root can be different. For example, we can first visit the right subtree, then the root, and then the left subtree. Or we can first visit the root and then the left subtree and then the right subtree. Conventionally, left subtree is always visited before right subtree. With this constraint, we will have three permutations. We can first visit the root and then the left subtree and then the right subtree. And such a traversal will be called pre-order traversal. Or we can first visit the left subtree, then the root and then the right subtree, and such a traversal will be called in-order traversal. And we can also go left, right and then root, and such a traversal will be called post-order traversal. Left and right subtrees will be visited recursively in same manner as the original tree. So in pre-order, once again for the subtrees, we will go root, left and then right. In order, we'll keep going left, root and then right. The actual implementation of these algorithms is really easy and intuitive. Let's first see code for pre-order traversal. I've first written the algorithm in words here. In pre-order traversal, we first need to visit the root, then the left subtree, and then the right subtree. Now I want to write a function that should take pointer or reference to root node as argument and print data in all the nodes in pre-order. Let's say visiting a node for us is printing the data in that node. In C or C++, my method signature will look something like this. This function will take address of the root node as argument. Argument type is pointer to node. I'll define node as a structure with three fields like this. Data type in this definition is character, and there are two fields to store the addresses of left and right children. Now in pre-order function, I'll first visit or print the data in root node, and now I'll make a recursive call to visit the left subtree. I have made a recursive call here, and to this call I'm passing address of the left child of my current root. because left child will be the root of left subtree, and I'll have another call like this to visit the right subtree. There is one more thing that we need to add in this function and we will be done. We cannot go into recursion infinitely. We need to have a base condition where we should exit. If a tree or subtree is empty, or in other words, for any call if root is null, we can return or exit. Now with this much of code, I'm done with my pre-order function. This will work fine in C or C++. Actually, in C, make sure you write struct space node instead of writing just node. Rest of the things are fine. It will be good to visualize this recursion. So let's now quickly see how this pre-order function will work if this example tree that I'm showing in right here is passed to it. I'll redraw this tree and show it like this. Here I'm depicting node as a structure with 3 fields. Let's say the leftmost cell here is to store the address of left child, the cell in middle is to store the data, and the rightmost cell is to store the address of right child. Now let's assume some addresses for these nodes. Let's say the root node is at address 200, and I'll assume some random addresses for other nodes as well. And now I can fill in left and right fields for each node. And as we know, the identity of tree that we always keep with us is reference or address of the root node. This is what we pass to all the functions. In our implementation, we often use a variable of type pointer to node named root to store the address of root node. We can name this variable anything. We can name this variable root, or we can name this variable root ptr, but this is just a pointer. This particular block that I'm showing here is for pointer to node, and all these rectangles with 3 cells are nodes. This is how things are organized in memory. Now for this tree, let's say we are making a call to this pre-order function. I'll make a call to pre-order passing it address 200. For this call, root is not null, so we will not return at first line in this function. We will go ahead and print the data in this node at address 200. I'll write output for all print statements here. And now this function will make a recursive call. Execution of this particular function call will pause. It will resume only after this recursive call pre-order 150 finishes. This second call is to visit this left subtree. This call pre-order 150 is to visit this left subtree. Address of the left child of node at 200 is 150. Once again, for this call, root is not null, so we will go ahead and print the data. Data in node at 150 is D, and now once again there will be a recursive call. With this call pre-order 400, we are saying that we are going to visit this subtree. Once again we will print the data and make another recursive call. Now we have made a call to visit this particular subtree with just one node. For this call we will print the data, and now for node at 250, address of left child is 0 or null. We will make a call pre-order 0, but for this call we will simply return because the address in this variable root will be null. We have hit the base condition for our recursion. Call to pre-order 0 will finish and pre-order 250 will resume. Now in this particular function call, we'll make another call for right subtree. For node at 250, even the right child is null. We will have another recursive call passing address 0, but this once again will simply return. And now call to pre-order 250 will finish and call to pre-order 400 will resume. Now in call to pre-order 400, we will make another recursive call to pre-order 180. With this call pre-order 180, we are visiting this particular subtree with just one node. For this call, first we will print the data and then we will make a recursive call to pre-order 0. Now pre-order 0 will simply return, and then we will have another call to pre-order 0 for right child of 180. The recursion will go on like this. There is one thing that I want to talk about here that's happening in this whole process. Even though we are not using any extra memory explicitly in our function, because of the recursion, we are growing the function call stack. We have discussed memory management a number of times in our earlier lessons. You can check description of this video for a link to one of those lessons. As we know, for each function call, we allocate some amount of memory in what we call stack section of application's memory. And this allocated memory is reclaimed when the function call finishes. At this stage of execution of my recursion for this example, my call stack will look something like this. I'm writing P as shortcut for pre-order because I'm short of space here. Let's say we made a call to pre-order passing it address 200 from main function. Main function will be at bottom of stack. At any time, only the call at top of stack will be executing and all other calls will be paused. Call stack keeps growing and shrinking during execution of a program because memory is allocated for a new function call and it's reclaimed when a function call finishes. So even though we are not using any extra memory explicitly here, we are using memory implicitly in the call stack. So space complexity, which is measure of rate of growth of extra memory used with input, will depend upon the maximum amount of extra memory used in the call stack. I'll talk about space complexity once more later. For now, let's come back to this recursion that I was executing. Call to this pre-order 0 will finish and pre-order 180 will resume. Memory allocated for execution of pre-order 0 will be reclaimed. Now for pre-order 180, both recursive calls have finished. So this guy will also finish. Even for pre-order 400, both calls have finished. So pre-order 150 will resume. Now this guy will make a recursive call to pre-order function passing it address 450, address of its right child. Memory in the stack will be allocated for execution of pre-order 450. Now in this call we will first print the data and then we will make two recursive calls to pre-order passing address 0 each time because for this node at 450 both children are null. Both calls will simply return and then pre-order 450 will finish. And now pre-order 150 will also be done. If you can see, the call stack will grow only till we reach a leaf node, a node with no children. And then it will start shrinking again. Maximum growth of call stack due to this recursion will depend upon maximum depth or height of the tree. We can say that extra space used will be proportional to height of the tree. Or in other words, space complexity of this algorithm is big O of h, where h is height of the tree. Okay, coming back to the recursion, we are done with pre-order 150, so pre-order 200 will resume. And now we will make a call to visit this particular subtree. In this call, we will print j, and then we will make a call passing address 60. So now we are visiting this particular subtree. Here we will first print g, and then this guy will make a call to pre-order 0, which will simply return. And then there will be another call to pre-order 500. Here we will print I, and then we will make two recursive calls passing address 0 every time because node at 500 is a leaf node with no children. After this guy finishes, pre-order 60 will resume. Now this guy will also finish and pre-order 350 will resume. And now we will have a call to pre-order 700, which once again is a leaf node. So k, which is data in this node, will be printed. And then we will make two calls passing address 0, which will simply return. Now at this stage, all these calls can finish. We are done visiting all the nodes. Finally, we will return back to the caller of pre-order 200, which probably would be the main function. So this is pre-order traversal for you. I hope you got how this recursion works. Code for in-order and post-order will be very similar. In in-order traversal, my base case will be the same. So I'll say if root is null, then return or exit. If root is not null, I first need to visit the left subtree. I'm visiting the left subtree with this recursive call. Then I need to visit the root. So now I'm writing this printf statement to print the data. And now I can visit the right subtree. So this second recursive call. And this is my in-order function. In-order traversal of this example tree that I have drawn here will be this. This particular binary tree is actually also a binary search tree. And in-order traversal of a binary search tree would give us elements in the tree in sorted order. Okay, let's now write code for post order. For this function, once again, the base case will be the same. So I'll say if root is null, return or exit. If root is not null, I first need to visit the left subtree. So I have made this recursive call. Then the right subtree. So I'll have this another recursive call. And now I can visit the root node. Post order traversal for this example tree will be this. So this is pre-order, in-order and post-order for you. You can check the description of this video for a link to all the source code. Let's now quickly talk about time and space complexity of these algorithms. Time complexity of all these three algorithms is big O of n. If you could see, then there was one function call corresponding to each node where we were actually visiting that node, where we were actually printing the data in that node. So running time should actually be proportional to number of nodes. There is a better formal and mathematical way of proving that time complexity of these algorithms is big O of n. You can check the description of this video for a link to that. Space complexity, as we had discussed earlier, will be big O of h, where h is height of the tree. Height of a tree in worst case will be n minus 1. So in worst case, space complexity of these algorithms can be big O of n. In best or average case, height of a tree will be big O of log n to the base 2. So we can say that in best or average case, space complexity will be big O of log n. I'll stop here now. In coming lessons, we will solve some problems on binary tree. Thanks for watching.
Okay.
video, I want to cover the basics of what is a linked list. A linked list uses data structures. So if you have a structure, say, let's take a simple case. You have a bunch of friends and you want to keep track of them, and you want to keep track of their first name and their age. We're going to keep it easy so I don't have to draw a lot. So let's say you have a structure, and I'm not going to write the structure, but the structure has a string that has the first name, so we'll pick a name here, and an age. Now what your structure is also going to have is a pointer to another structure of the same type. So you're going to have, say, the next pointer in here. I'm just going to call it next. I'm not going to put a star in front of it or anything because I'm just talking about the concept of what is a linked list. So here's one data record for one person. Name is John, age is 46, and then there's a pointer to the next. So let's say you start this, your program is going to add these things to this linked list. So you start with the first one, John, 46. You've just got one person. Now when you bring in another person, let's say you have Susan, age 20. She's got a next pointer. What a linked list does, let's say this is going to go in alphabetical order, so Susan comes after John. So you're going to set this next pointer to point to this block of data. And Susan is the end of the list, so she points at what's called null. And you've also got another pointer called typically head for the head of the list or the start of the list, and that's going to point to the structure that has your first record. So here this linked list right now only has two elements. So when you want to search through your list for a certain person, you start at the head pointer here and you look at the first structure. You say, okay, my first person is John. Well, that's not who I'm looking for, so I'm going to follow this next pointer to the next block and head over to check out the next block, which is Susan. Maybe that's not who you're looking for either, so you go to the next pointer and you say, oh, okay, I hit null, I'm at the end of my list, I didn't find who I was looking for. So that's very simple, just a two-element linked list. Let's say you want to add another person, and this guy is going to be, we'll make it so it goes in between these two, say Carl, and he's 34, just for grins. And he's got a next. So now what happens? You have to traverse through and find where this guy goes in your list. So you start at this head pointer up here. You go here, you look at the name, John. Well, John is before Carl, so you have to keep looking. You go to the next, travel over here to the next. You see the next one is Susan, and you can tell, okay, Carl is before Susan, but after John. So Carl needs to be inserted in between these two. So the way you would do that in the code is you say, okay, Carl's next pointer, well, I know Susan has to come after Carl. So Carl's next pointer is set equal to be Susan, because we know that's next. And then John's next pointer now, instead of going to Susan, it comes over here and points to Carl. Okay, so now this pointer is no longer pointing to Susan. It is now pointing down to Carl. So when you want to traverse your list, you're going to search for somebody. You start again up here at the head pointer, up here. Go to your first record. Examine who's there. If it's not who you're looking for, you travel along the pointer to the next record. If that's not who you're looking for, you travel along the next one. And if that's not who you're looking for, you travel to the next one. And when you hit null over here, you know, okay, I've hit the end of the list. I'm done searching. So that's kind of the essentials of what is a linked list in basic terms. So you've got different operations you'll do on this linked list. For instance, inserting a block, as we just saw. You want to be able to delete a block. start from the head up here again. Traverse through. Bigger than John, bigger than Carl, bigger than Susan. You see the null here, which wasn't taken away yet, even though I erased it. I say, okay, I got to the end. I didn't find my insert point, so therefore Zoe here has to go at the very end. So what you would do there is you say, okay, well, her next pointer is now going to point to null because she's at the new end of the list. And then Susan's pointer, instead of pointing to null, is going to be reset to point to Zoe. And that's kind of the crux of how a linked list works. So you can imagine what you need to do when you want to delete an item. So say you want to delete Susan. You start from the head up here again. You traverse through until you find a match. Come over here. Okay, you find a match with Susan, and you need to delete. So essentially all you need to do there is Carl, who used to point to Susan, now needs to point to who is after Susan. So Carl's pointer here gets reset to point over here. And then this pointer is no longer pointing to Susan, it's now pointing to Zoe. So that's the basic idea of a linked list. You've got blocks in memory, which are structures in C, that have the data you're interested in. And then you've got a pointer to another block of that same type that ties them together however you want to tie them together.
Years of sorrow, lacking all emotion, staring down the barrel, waiting out to me if I deserved this feeling. I thought that you know that we had something special till you end up all this way. Please tell me when you left me bleeding. With a broken heart, tell me why I deserve this feeling. I thought that you loved me, I thought that you need me till you end up all this way. Have you forgot all the moments while we had was so true? This world was made for two.
high school was hard. You'd fight with my mom. I'd fall asleep to the screaming, sound machine always speaking, left emotional scars. Now I'm 21, a soul of 50 years. And now that you are gone, I'm doing things that I shouldn't know from. I'm doing things that I shouldn't do. At 21, a soul of 50 years. And now that you are gone, I'm doing things that I shouldn't know from. I'm doing things that I shouldn't do. At 21. At 21. I'm doing things that I shouldn't do. At 21. I'm just a kid. Oh, I'm doing things I shouldn't know from. Yeah, doing things I shouldn't do. At 21. Yeah, I play you my favorite songs on a car ride while you list me all the people that left you in your life. Oh, oh, oh. And you smoke on your chair while I was trying to sleep. I smell the smoke in the air, but that was normal for me. I didn't know. I didn't know. But now I'm 21. A soul of 50 years. And now that you are gone, I'm doing things that I shouldn't know from. I'm doing things that I shouldn't do. At 21. Feels like I'm 50 years. And now that you
Bueno, vamos a crear un repo para esto. Esto es linked list. Publicarlo. Privado no.
You are so heartless, and you don't care. And I don't even know what I've been fighting for. You got me hoping, and you don't care. And I don't even know what I've been fighting for. Every time I fall in the deep, and I can't fight it, I can't fight it. You wreck my mind, I'm losing my
Usar mi buen amigo ChatGPT.
so don't leave me alone.
A ver, create. Ok.
Won't you say why you're a stranger now? Your eyes escape mine when I sit you down. Don't you feel like we're holding on onto a fairy tale, but the magic's gone? Been months of buffing the blushes and faking the butterflies. Wake up, yeah, I'm kicking the castle down.
Ok, me pide que contiene un value property data. Ok, eso está. Append, prepend. Eso lo tengo. Append, prepend. Return size, side head tail. Append, esto tengo, prepend, me lo creo. At the first size, remove, get empty size print. Okay. Size, head, tail. A ver si si la pegamos con eso.
I just can't let you go. Lord knows that I've tried to. You said I was the only one. No one likes being lied to.
Beginning of the list.
You made this mess and left me with the pieces. Now I wanna burn all the bridges between us.
Okay, insert now the specific position. Eso no cambia.
I've been stuck on your memory, but it's not like I need it. And we may have some history,
Add index.
but we don't have to repeat it.
Tengo un index.
You made this mess and left me with the pieces. Now I'm gonna burn all the bridges between us. I can't focus. I can't.
Creo que es el get que tengo acá.
I've been thinking too much lately. I just need to clear my. I just need to clear my head. I just need to clear my head. I just need to clear my head. I
Ok. At index, vamos a poner ejemplos get es at index.
They say that love is blind, but I never trusted sight. When I turn and look inside, there's nothing I can't find. In the silence of the night, when my demons come alive, I hear a voice disguised, telling me we're not alright.
Current. Ok. Pop, remove last element from the list. Pop creo que estaba puesto.
They say that love is blind, but I never trusted sight. When I turn and look inside, there's nothing I
Específico.
in the silence of the night. When my demons come alive, I hear a voice disguised, telling me we're not alright.
Pop. Ok. Pop.
You say my name, you thinking it out loud. But I love those days when there's no one else around. I can feel your heart close to mine. In the night, we sleep talking about you with me. I could die just thinking about you when you're not with me. All this time, you fill my head and all my daydreams of you. In the night, we sleep talking about you with me. I could die just thinking about you when you're not with me. All this time, you fill my head and all my daydreams of you. 'Cause I know, 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 'c you and you're not with me. Oh, this time you fill my head and then my daydreams of you. In the night, we sleep talking about you with me. I could die just thinking about you and you're not with me. Oh, this time you fill my head and then my daydreams of you.
Yeah, I've been trying to get off this couch for a minute and a whole damn week. No kidding, I'm skinny, I cannot eat. Got a million that depend on me. Yeah, every friend in my family, from a girl, every fan I meet myself. I'm too on till I'm too off. Come down to make new thoughts, like jumping off of that rooftop. Whole life ever when I do nothing to make moves based on my mood drops. Like who's lost? Like who's lost? It's yo, stop. Steadily killing me, running my brain full of shame. I don't wanna lose it. Full of stage, trying to find my pain. See the sun coming out of that rain. My team really not tame. I'ma never slow down. I'ma never behave. Stuck inside this prison, inside this cage, it's taking over. Yeah, I'm a slave for you. Slave for you. Ripping harder, more less. Never stop, no rest. Till the stress is breath in my chest. Till it's diamonds wrapping my neck. Progress to a god from a god. Mess, hopeless, more tests. More blessed. Dug deep down, trying to find my best. Find a beast, had to kill a conquest. I'm next. I'm too on till I'm too off. Come down, make new thoughts. Like jumping off of that rooftop. Whole life ever when I do nothing to make moves based on my mood drops. Like who's lost? Like who's lost? It's yo, stop. Steadily killing me, running my brain full of shame. I don't wanna lose it. Full of stage, trying to find my pain. See the sun coming out of that rain. My team really not tame. I'ma never slow down. I'ma never behave. Stuck inside this prison, inside this cage, it's taking over.
Mm. Ok, vamos a darle crédito a... vamos a darle un formato más... Ok.
In the corner of the room, not ready to resume, 'cause I can't take it. Don't wanna be alone, but I'm not in the zone. I'm looking for somebody. I'm looking for somebody.
Ok, bueno, eso lo voy a estar corrigiendo después, así que, pero bueno, más o menos está quedando. Nada, hasta acá el stream y nos vemos después a la noche quizás. Saludos.